Everybody, welcome back to another fun and exciting pre-calculus class. Today we'll be in lesson 13.4 in your books. That's on page 270, so you can go ahead and open up there. And actually, I'm going to kind of teach from the book a little bit more than I normally do. So let's go ahead and jump right into it. Quadric surfaces. What is a quadric surface? Well, it should just kind of jump into your mind. Okay, quadratic, quadric, they sound pretty close. Well, you're right. These are all different surfaces that have some sort of a square in them. And because we've been talking about three-dimensional objects, then it should kind of make sense that these are three-dimensional, quadric, or squared surfaces. So what is this going to look like? Basically, this is going to look like several different surfaces, several different curves coming together into one shape. All right, so let's go ahead and look through these different ones. The first one here, table B, is called the ellipsoid. Now, an ellipsoid kind of makes sense, right? The ellipse, we know what the ellipse is. So an ellipsoid is just the idea of an ellipse, two ellipses kind of coming together and becoming one shape. So there you go, we have a couple of ellipses coming together to form the ellipsoid. The traces of the ellipsoid are all ellipses, so that should make sense again. If any of the two values a, b, and c are equal, the ellipsoid may be called an ellipsoid of revolution. It may be obtained by revolving the ellipse about its axis. The sphere, okay, check this out. This is actually another shape. This is a type of ellipsoid. Just like the square is a type of a rectangle, right? The sphere is a type of ellipsoid. The sphere is a special case ellipsoid where A equals B equals C. All right, so in right here, these are the important things right here. This equation right here is the important part of the ellipsoid. So connect ellipsoid if you're writing notes, and you should be writing notes. The ellipsoid, connect it with this right here. You don't necessarily have to write this in your book, but it may be worthwhile for you to try to work on making those shapes in your notes. All right, the next one is table C, the elliptic paraboloid. What is the elliptic paraboloid? They are ellipses and parabolas. Makes sense, elliptic paraboloid. There you go, there's the two words right in the name. If the squared denominators are equal, the traces are circles, and parabolas making the surface is a circular paraboloid. This one right here tends to look to me like a circular paraboloid. It could be longer or fatter or something and look more like an ellipse, but this one here looks pretty circular. This would be, kind of an example of these, and they give you some examples down here, but some reflector collector dishes, such as satellite dishes, are in the shape of a circular paraboloid. Another thing that I think of is like a hat, like a baseball cap. It's like a paraboloid. Now, it has like a bill off the front of it, but the thing that actually sits on your head is like a elliptic paraboloid. Okay, so yeah, different things in nature, you see these, and then man-made things as well. So table C, elliptic paraboloid. Next, let's go to the next page. We're on page 271. We did these in the last lesson, and if you maybe thought, wow, you just really skipped over that really quick. I said hyperboloid of one sheet, but I didn't really talk about it, and there's a reason why. Because it was coming up in this lesson. I don't really like it when the book does that, right? I kind of wish this lesson was before the last lesson, but here we are. And so they introduced it in the last lesson, but here they are teaching it in this lesson. The traces of the hyperboloid of one sheet are ellipses and hyperbolas, okay? And we had this one. We actually did one of these in the last lesson. The first equation is for the graph shown. The others have graphs oriented along the x and the z axis. So nuclear cooling towers are sometimes constructed in this shape. Notice this, when the 1 is replaced with 0, the equations represent a cone. So just like the sphere was kind of underneath of 1, the cone is going to be underneath of the hyperboloid of one sheet. All right, so here we go, and this should look somewhat familiar, like except with the z term. We've had this before. And, so these are just kind of now we're building on what we've already been seeing. Add the z term equals 1, and that's going to give you this looking thing right here. Now notice if we make the first one negative, all that's going to do is it's going to change the way the shape is kind of forming. And then if we make the z, then it's just going to go on to the other axis. So basically, whichever one is negative, so this one is along the y-axis, right? This one is along the x-axis, so we would turn it like this. And then this bottom one is along the z-axis, so we'd turn it like this. And it's just kind of a matter of which one is it wrapping around. See, this one is wrapped around the y, and then, the x and the z, respectively. The next one is the hyperboloid of 2 sheets. Now, the only difference here, it's the same exact thing, except notice they don't touch each other. Look, this one's touching, okay? It's kind of like the two things are mashed up against each other, and this one, they're not touching. There's a little bit of a separation. So it's different from the hyperboloid of 1 sheet in that it has 2 separate pieces. The first equation's graph is shown. The others have graphs oriented along the x and the z axis, respectively. Hyperboloids of 1 and 2 sheets may have traces that are circles instead of ellipses. So basically, here's what this is. Look at this right here, hyperboloid of 2 sheets, and then go back and look at what we dealt with over here, the elliptic paraboloid. All this is taking this elliptic paraboloid and putting another one underneath it facing the other direction. Now notice what changes here. We have a negative and a negative. Okay, in this one, notice the y is negative, and in this one, the y is positive. The x and the z are negative, and here the x and the z are positive. So if you'll take this hyperboloid of 1 sheet, change all of its signs on the left side, then you're going to get the hyperboloid of 2 sheets. Okay, and then the last one that we have to deal with here is the hyperbolic paraboloid. All right, the traces for this one are hyperbolas and parabolas. It is the most challenging quadratic surface to graph. The first equation is for the graph shown, and then we would rotate it 90 degrees, and that would kind of basically be the next two, kind of just rotations of it. So if you look at this and then look over here, you might say, oh, that's interesting. That looks like a Pringle. Yes, that looks like a Pringle. And most of the time, I will give Pringle this. I like them for this. Most of the time, all the way from the top to the bottom, they are in, they're whole chips. They're not like the bottom of the bag of chips where it's just all crumbles. Every once in a while, especially if one of your little brothers or something like shakes the thing up, it's going to break them. But these things are pretty rigid. Notice that it says some potato chips are manufactured in this shape for rigidity. So it makes them stronger so they don't crack and break in the transit, going from the store to the house and things like that. So this shape tends to keep them in order, intact. So there you can, if you think about this, this might also mean that there's a lot of rigidity in a structure that's built with this. So if you think about maybe some bridges or different things that you've seen with this kind of basic idea, this concept right here, they're very strong. I told you this lesson was going to be a little different because there are no example problems. It goes right into your exercises. So I really want to just jump into a couple of these. I want to do a couple of them with you just so you'll know what's going on. It says find the trace equations on the coordinate planes as well as the planes indicated, name, shape. Okay, so basically what we want to do is we want to take this and break this down into its base equation. So let's jump over here and look at this right here. I've got it written down, and let's break this down. So what is this going to look like? All we're going to do here is we're going to try to get this to go to 1. Okay, so we're going to divide this by 25, by 25, by 25, by 25. Okay, and so that is going to now give us x squared over 25 plus y squared over 25 plus z squared over 25 equals 1. There we go. That's in standard form. Now what we would have to do is kind of go back over to the book, and we can jump back over here and we can look at which one does this look like. Well, this looks like this first one right here. X squared over a to the x squared. Notice if we kind of flip back over here, we do have a squared down here, right? So we could break that down and make it look even more like that by going x squared over 5 squared plus y squared over 5 squared plus z squared over 5 squared equals 1. Okay, so I just basically broke down that 25 into squared units. And look back over here in the book. So you'll see x squared over a squared, y squared over b squared, z squared over c squared equals 1. This is the thing that we have. We have an ellipsoid. Now we also have a special ellipsoid. Notice it says the sphere is a special case ellipsoid where a equals b equals c. So jumping back over here, notice that a equals b equals c. Since all of those are equal, we end up with a sphere. Now let's check this out on the GeoGebra calculator, graphing calculator that I showed you. So when we put this in, here it is right here, a squared plus y squared plus z squared equals 25. I put the original. I didn't put it into, kind of standard form, but we could do that. We could divide this out. It'd look the same once we did that. So here's our sphere. And if you'll notice, it looks the same in any direction that I put it because it's a sphere. So it doesn't matter how I rotate it, it still looks like a ball. There's no change to the shape. All right, let's jump back over here to the book. Let's do one more. That was so much fun. Let's do one more. And I'm going to kind of just jump around here. Now it says down here, name and sketch each of the following surfaces. And to be honest, I didn't complete this. Okay, so I didn't finish number 1. I just kind of jumped to show you what the sketch looks like. There's more to do with number 1. So one thing that we did not do is we did not find the trace equation. How do we do that? Well, the trace for the x would be when you take x out, and what is the rest of the equation look like? We just didn't go through that, but that was from last lesson, so you should remember how to do that. All right, so let's do number 16 down here. We need to name and sketch each of the following surfaces. Notice it's saying sketch. It does not say to graph. You do not have to graph these. You have to sketch these. Now, I would sketch them on graph paper, but it doesn't have to be perfect. So just name it and sketch it. So number 16 is negative x squared plus y squared minus 4z squared equals 4. Let's do that one. Let's see what we come up with. All right, so over here we have the equation that we have for number 16. And what we want to do is we want to try to get this into some sort of a standard form. The way that we can do that is divide everything by 4. Okay? And this is going to give us as close as we can get it to standard form. Then hopefully it will look like one of the other forms that we had. So we're going to have over here, we're going to have x squared. It's going to be a negative x squared over 2 squared. Okay. Now this one cancels out, and so we end up with just y squared. You could say y squared over 1 squared if that helps with the way that it looks. And then this one we're going to have a negative. That's going to cancel out, and we're going to have that z squared over 1 squared equals 1. Now the reason I wrote these is because a lot of times in the standard form that we have them in, we're going to need that denominator. So in this case, we're going to have an a, b, and c. So that 2 is going to be the a, the 2 underneath the x, and so on. So let's go back to the book and let's see if we can find one that looks like this. All right, so the ellipsoid doesn't really look like that because we have some negative signs. Remember, our x is negative and our z is negative. So then when we come down here and look at this next one, the elliptic paraboloid, I don't see any negatives here. I don't think that one's going to work. Let's come over here. The hyperboloid of one sheet. I have a negative here, but that's just our y, and our y was positive. Okay, in this one we have an x that's negative, but look, our z is positive, so that's not it. And that one, z is negative, but x is positive. All right, let's check this one out. All right, negative x, positive y, negative z. I think we're onto something right here. Equals 1. This looks like what we have. So we would have a hyperboloid of 2 sheets, and then when you sketch it, you would just sketch it out kind of based on the information that you see. What's the information that you're seeing? You're seeing kind of a denominator of 2, other denominators of 1, and then you would try to make that kind of match out on your paper. Let's go ahead and put it into GeoGebra and see what we get. All right, so let's go ahead and enter that. We had a negative x squared, and that was divided by 2. And then we had a positive y squared. And we don't necessarily need to write the divided by 1 that we had. It'll be fine, minus z squared. And then we are going to set that equal to 1. And there we go. There's our new shape. This is what we're looking at, and it's exactly what we thought it was, right? So let me try to rotate this in so you can see it, so it kind of looks like the one in your book. And so there you go. There's the hyperboloid of 2 sheets. This comes down. And so there you go. That's what it kind of looks like when you graph it out. All right, that's all I've got for you in this lesson. Hopefully you learned something there. Hopefully you're kind of piecing this stuff together and it's making just a little bit of sense to you. You know, this is not easy stuff. If it was easy, it would not be called Precalculus. So hopefully you're working hard here. You're really digging in. You're memorizing these things. You're learning those different standard formulas that you need for all those different shapes. And then you're able to kind of be able to pick out which one is which. That's all I've got for you. Hope you have a good one. If you missed anything, slide it back, watch it again. We'll see you later. Have a good one. Bye-bye.